In this section, we are going to be learning about state machines. State machines are a type of sequential circuit. Why are they called a state machine is because they switch between a finite given set of states in a sequential fashion. So the simplest example I can give you for a state machine is the counter, which you must be familiar with. So when you construct a counter, let's say a 3-bit binary up counter, it has a set of states which are 000, 001, so on up to 111. So there are 8 possible states, and so the set of states is finite and it's a given set, meaning it is not any possible random state. There are well defined states, meaning if it's a 3-bit counter, it will count from 0 to 7. So the possible states are the binary representations of the numbers 0 to 7. So the states it can take are well defined and they are finite, and it moves in a sequential fashion. So if it's an up counter, it will move 0, 1, 2, 3 up to 7. If it's a down counter, the opposite direction. Or if it's an up down counter, it will do both 0 to 7, 7 to 0, 0 to 7, 7 to 0, and so on. So that is an example of a state machine. So a state machine is something which switches between a finite set of states in a sequential fashion. The sequence need not always be something like 0 to 7, 7 to 0, forward, backward, but there are rules which help you identify from this state under what conditions which state will it go to. So if those rules are well defined, you call that circuit a state machine. So to design a state machine, we have 4 steps. The first is to draw the state diagram. If it's a counter or something like that, you draw the state diagram because you know how the you know the states and you know the sequence in which it is going to progress. If it is some randomly designed state machine, you might be given with the state diagram. So in any case, the first step, you need to have the state diagram at hand. Second step is something called reducing states. So there are equivalent states in a state machine, there might be. So we will be reducing that. So we are going to be looking at state reduction in detail in this video. After that, you draw the state table. You use the excitation table to fill up the flip-flop inputs. You use the K-map to get the expression, and finally you draw the circuit diagram. These last 2 steps I have explained in detail when I did a lecture on how to design a counter. A 3-bit binary up counter was the example I took, and the last 2 steps are exactly the same as followed in that one. So if you have not watched that segment, I would recommend you to watch that after this one, because in this one we are going to be focusing mainly on state reduction. So to summarize what we know about state machine, it has a finite number of states and it progresses from one state to another in a sequential fashion. And by sequential, I mean that given the current state and given the inputs, you know what the next state is going to be. There are well defined rules which help you identify that. And the 4 steps are to have the state diagram, reduce states, and then you get the state table, the K-map, the expression for the flip-flop inputs, and you draw the diagram. So in this section, we will be looking at state reduction in detail. So what is state reduction is, in a state table, sometimes you might have equivalent states. So if you take a counter, which is the example I gave for a state table, let's say a counter that goes from 0 to 7, all the 8 states are unique. But there are state machines where the states are given in terms of like A, B, C, D and so on. They are not specific numbers. And you have conditions like if it is currently at A and if I give you an input 0, it goes to B. If I give you an input 1, it goes to C and so on. So those are a variant of state machines which we will be looking at. So because the states there are defined in terms of A, B, C, D, it is possible that there are 2 states which lead to the same output under every combination. For example, let's say I have a state A. If I give you an input 0, it gives me an input 1 and takes me to B. If I give an input 1, it gives me an output 0 and takes me to C or something like that. And if there is another state D which also does the same thing, D input 0, output 1 goes to B, D input 1, output 0 goes to C. For example, if it does the same thing as A, then I can say A and D are equivalent states. So I can replace D with A. So instead of having two states A and D, wherever I have D, I can replace it with A and bring it all in terms of A. So two states are said to be equivalent if and only if for each input combination they give the same output and send the circuit to the same state or to an equivalent state. And if a state diagram has two equivalent states, they can be condensed into one, which is what I just explained, and we will understand this better when we look at an example. So this is an example of a state diagram that might be given to you. This is, if you can see, it looks slightly different from the state diagram for the counters, because firstly the states are defined in terms of A, B, C, D, E, F, G and not 0, 0, 0, 0, 0, 1 and so on. Secondly, there are certain values 0 bar 0, 1 bar 0 and so on. So I'll first tell you how to make sense of this diagram and then we'll go about with state reduction. So for every arrow there will be two numbers separated by a slash. So the first is the input, the second is the output, and the loop represents the current state and the next state. So let's say A, loop or arrow A, arrow B, 1 bar 0, meaning my current state is A. If I give an input of 1, my next state will be B and an output will be 0. So in a counter you do not have this external input or output, so your state itself is the output. So if it is a state of 0, 0, 0, it's just going to display 0, 0, 0. So a counter is a simple example of a state machine, but these are slightly more involved ones where you have a current state and a next state, but apart from that you also have an external input and an output. So again, current state B, if I give an input 0, it will take me to C and it will give me output 0. Current state F, if I give an input 1, it will take me again to F only and it will give an output 1. Current state E, if I give an input 0, it will take me to A with an output 0 and so on. So how do we make sense of the diagram? Current state, the next state upon giving this input, and it will give me this output. So this is the state diagram. From this, to perform state reduction, that is to identify if we have any similar states, we need to fill this thing called the state table. So current state is A. So we'll look at the diagram and try to fill. Current state A. If x equals 0, what will my next state be? Current state A. If my input is 0, the next state is going to be an A and the output is also going to be a 0. So if x equals 0, next state A and the output is going to be a 0. If x equals 1, my next state will be a B and the output is 0. Current state A, if the input is 1, x is the input here, next state B, output is a 0. Similarly, current state B, if my input is 1, what will be my next state and output? Let's see. Current state B, if input is 1, the next state is D and the output is a 0. D, output will be a 0. Current state B, input 0, next state will be C, output will be 0. C, 0. So going by the same logic, we need to fill up the entire table. Once we have done that using the state table, this is what, using the state diagram, this is what the state table looks like. Now, the idea we started out with was state reduction, right? Meaning I want to identify if there are any identical states, equivalent states, and remove the unnecessary or redundant ones. So, how do you identify equivalent states is, if their values are the same, as in for every input, it takes me to the same state and it gives me the same output, then I say these two states are equivalent. So if you observe this table, you will identify that the states D, I'm sorry, this one has to be an AF01, I'm sorry, because G goes to A, yeah. So now if you observe the table, you will note that E and G are equivalent states. So when I take state E and I give it an input of 0, it will take me to A and give me output 0. If I give an input 1, it takes me to F and gives me output 1. And G does the same thing, input 0, next state A, output 0. Input 1, next state F, output 1. So E and G are equivalent states. So you can choose to retain one of them and discard the other. So let's say I choose to retain E and discard G. So what I do is, wherever there is a G here, I will replace it with E because G is equivalent to E. So let's look for all the G's we have here. There's only one G. So I remove the G and replace it with E. So this is my reduced state table after the first step. And this state no longer exists. So formally, when you're doing this on paper, after every reduction you need to draw the state table again and show. So after the first reduction, your state table will have these 6 rows and there would be an E here instead of the G. I am doing it on the same table so that you're able to understand better, but of course conventionally you need to draw it again. So now we have A, B, C, D, E, F, 5 states. So let's see if there is anything else that can be changed again. This is an EF01, EF01. So again we can see that D and F are equivalent states. So let us choose to retain D and ignore F. So wherever there is an F, we will replace it with a D. So there's an F here, there's an F here, I make it D. So this is what my state table looks like now. Any other F's? No. So again, compare to see if there's anything else that is common. AB00, CD00, AD00, ED01, AD01. Meaning there are no equivalent states now. So this is your final reduced state table. So you repeat the same state reduction until you are sure that there is no more reduction possible. There are no more equivalent states. Now finally, from this state table, we draw the state diagram. So we have 5 states, A, B, C, D, E, and A. If I give an input of 0, it goes to A with 0. So A goes to A 0 by 0. If I give an input of 1, it goes to B with 0. So A to B, input 1, output 0. B, input 0 goes to C, output 0. B, input 0 goes to C, output 0. B, input 1 goes to D, output 0. So input 1 goes to D, output 0. Similarly, C, input 0 goes to A, output 0. C, input 0 goes to A, output 0. I am sorry about the very shaky diagram. And input 1, D, 0. So if you get C, input 1, D, 0. Similarly, you take for D and E and we complete the state diagram. So when we take the reduced state table and draw a state diagram, this is what our final reduced state diagram looks like. Now once this has been done, we will assign numeric values to each of the states arbitrarily, because your circuit can only work in terms of zeros and ones, right? So it cannot show an A or a B. So we start assigning values from 0, 1, 2, 3, 4 and so on. Because we have A, B, C, D, 5 states here, you will number them from 0 to 4. So let us say A equals 0, 0, 0, B equals 0, 0, 1, C is 0, 1, 0, D is 0, 1, 1, E is 1, 0, 0. You will assign these numbers to the states after performing this state reduction. Once this has been done, we say that the state reduction process is formally over. After that, what do? State table, K-maps, flip-flop input. So this is a picture of the state table for the 3-bit binary up counter, which I explained in a previous video. So this is how you draw the state table. Similarly, from 001, 000, 001, so on up to 100. I think those were the inputs. You draw the next state. You draw the external inputs and outputs as well. And then you derive the expression for the flip-flop. So I will give you a quick sample. I'm not going to go into the entire process in detail because it is, like I said, explained in a different video. But I'll just give you a quick look at how to fill the values. So if you look at the state table, or or rather, yeah, this diagram would help better. So let's say the current state is 0, 0, 0 or A. Then if I give an input of 0, it goes back to A with an output of 0, right? So current state 0, 0, 0, input 0, next state again goes to 0, 0, 0, output 0. Similarly, if it is current state is B and I give an input of 1, it goes to D with an output 0. B 0, 0, 1, input 1, it goes to D, which is 0, 11, 0, 1, 1 with an output 0. Similarly, you have to fill in the values for these columns for all possible states. So you have 5 states, and from each you will have an input 0 or input 1. So 5 into 2s are, you will get 10 entries in this table, 10 rows. And then once that is done, you will draw your K-map. Let's say you're drawing for J2, the K-map will take the 3 current states and the input as its value. So you will have Q2, Q1, Q0, X. So you will draw the K-maps. You will, of course, you will fill in these using the excitation table. You will get ones, zeros and don't cares. So you will put them in and you will do the grouping as usual. You will find out expressions for J2, K2, J1, K1, J0, K0 and for the output Y. So this is how we design a state table. This of course is assuming you are using JK flip-flops. So if it was a D flip-flop, then you would just have D3, D2, D1. If it was a T flip-flop, it would be T3, T2, T1, T0, I'm sorry, and so on. So whatever flip-flop you're using. So I will give you a quick recap of everything we did. So the state diagram, first of all, was given to us. From that, we drew the initial version of the state table. And how do we read the state diagram? Current state, next state, upon giving this input, and it gives me this output. So using that knowledge, we filled up the state table. Whenever 2 states had the same combination of values, they were equivalent. So you cut one. Let's say E and G are equivalent, you retain E, you cut G. Wherever you have a G there, you replace it with E. And you get the revised state table. You repeat the same process until you are sure nothing can be further reduced. Now using this, you draw the reduced state diagram. From that, you give numeric values to the states. Now that is state reduction. Then to reduce, then you draw the state table using the current states, the input, next states, output, and the flip-flop values for whatever you're using, J, K or D, S, R, T, depends on what flip-flop you've been asked to use. So these values you will get from the reduced state table. And if there are 5 states and 2 inputs, you will get 5 into 2s are 10 values. So I've just filled 2 rows just to give you an example, but you will have to fill in all the entries. These you will look up from the excitation table, how you compare Q2 current and Q2 next, Q1 current and Q1 next, and so on, and you fill in the values by looking at the excitation table. How exactly that is done, I've described in the video where I spoke about counters. So once that is done, you need to draw K maps for J2, K2, J1, K2, K1, J0, K0 and for the output Y using the values here. You will do the grouping as usual and you will get expressions for all of these in terms of the current state and the inputs. And once that is done, you will draw the circuit diagram and connect them accordingly. So that is how you design a state machine.